Hello, I'm Hui-Ping Chen, a PhD student from King's College London. I will talk about breaking trust-based communities in graphs. This is a drawing work with Alessio, Roberta, Grigoris, Solon, and Michel. Graphs naturally model relationships between entities in domains such as social networks, communication networks, or the web. A fundamental data analysis task in this domain is community detection. This task employs a different notion of graph community, such as N-club, K-core, K-clique, and K-truss. In this paper, we focus on K-truss. A K-truss is a subgraph, which each edge is contained in at least K-2 triangles of subgraphs. For example, on the right, the red nodes form a 3-truss and the blue nodes form a 4-truss. The community structure is key property of a graph, so it's essential to study how it can be maintained or broken. Thus, we introduce a general problem we call community breaking problem or CB problem. So in this problem, given an undirected graph G, a subset of nodes U, and a notion of community, the problem asks to identify a smallest set of edges from G so that after deleting these edges, no community in G contains a node in U. The CB problem is motivated by the following application. The first one, identifying the critical edges for community in social networks. The second one is assessing resilience to attacks or errors in communication networks. The identified edges correspond to vital connection in the network. So third application is hiding the friendship in the social network so that the user are not seen as belonging to community, which could lead to user discrimination. The last application is preventing the detection of confidential communities by sanitize a graph before its dissemination. Based on the CB problem, we define two problems of practical importance. The first one is min K-CBS, which seeks the minimum set of edges incident to a given set of nodes U, such that no nodes in U is in a K-truss. And the second one is min K-TBS, which is a special case of min K-CBS, where U contains all nodes in the graph. For example, by applying min4 TBS on the left graph, we identify the edge with the right cross in the right graph. So removing this edge makes the graph 4-truss free. We observed that a graph from Twitter and Foursquare contained K-trusses, with many users whose check-ins may reveal religious belief or gambling habits. For example, more than 43% of users in the 24 trusts checked in to casinos or strip clubs. To avoid being discriminated based on homophily theory, this user can set some of their friendship to private, as in Weibo, a social network in China. And our min K-CBS identified a smallest set of friendship that this user can set to private. Please see the paper for result of applying our min K-CBS method in this setting. In this work, we prove that min K-CBS and min K-TBS are NP-hard and show a data structure for efficiently maintaining the trust decomposition of a graph. We develop an exact algorithm and 3 heuristics for these problems, and which use this data structure. Furthermore, we show a lower bound on the size of optimal solution to min K-TBS and an algorithm to compute it. Last, we present the experiment. So Min3 TBS is NP-hard as it's equivalent to the NP-hard problem of breaking all triangles in a graph. We show that Min-K TBS is NP-hard using a reduction from Min3 TBS. And then Min-K CBS is then clearly NP-hard since it has Min-K TBS as special case. We now introduce the two definitions that we will use in our data structure. The age trustness of an age is the largest K for which the age belongs to a K-truss. In this example, the largest truss which C belongs to is a 4 truss. Thus, TC equal to 4. And the age trustness helps us find a maximal K-truss. For example, a maximal 4 truss is formed by the edges with TE larger or equal to 4. The second one is the triangle trustness. The trustness of a triangle is the minimum age trustness of the edges of the triangle. For example, triangle CGH belongs to a 3 truss since the minimum TE among CG and H is 3. The effective of deleting an edge in a K-truss can propagate through the graph. The naive method to get the K-trusses after an edge deletion is to traverse the whole graph and recompute the truss decomposition. But this is expensive, so we introduce the truss decomposition update data structure. So first, our data structure maintains the triangles of graph. We list all edges and all triangles on the left side and the right side respectively, and then link each edge to the triangle that it belongs to. Also, we maintain the edge trustness and the number of triangles of different trustness that each edge belongs to in table T. In this table, each cell corresponding to the number of triangles of certain trustness to which an edge belongs in the current truss. For example, edge C is contained in 2 triangles, one red, one green, of trustness 4, and also one blue triangle of trustness 3. If we delete an edge A, we first update the triangle hash table, removing all triangles that contain edge A and also the link corresponding to these triangles. Then we update table T and edge trustness. So now I will introduce how we update the truss table and also the edge trustness. So first, we use a stack L to store edges whose trustness is to be updated and propagated. We repeatedly pop an edge from L and perform the following update operation until L is empty. The first one, we update the edge trustness of E if needed. And in here, we delete edge A, so TA equal to 0, and in the table, TA row is set to all zeros. The second operation is for each triangle that contains an edge whose trustness changes, update its entries in table T and put its edge into L. The benefit of our data structure is it's very good to amortize the time complexity of all in the trustness of G times the number of triangles in G. For deleting all edges instead of the all E in the power of 1.5 per edge deletion of the naive way of recomputing the truss decomposition after each edge deletion. Then we develop an exact algorithm which lists all minimal K trusses and find a minimum transversal in hypergraph, where each hypernode corresponds to an edge in graph G, and each hypernode corresponds to a minimal K truss in G, thus a hypergraph transversal corresponding to a solution in min K TBS. The exact algorithm can be modified easily to solve min K CBS, as we show in the paper. We also develop heuristic. Our MBH heuristic iteratively remove an edge from the maximal truss of G until there's no K truss. So the first of this heuristic is MBHS. Select an edge contained in the largest number of triangles in the maximal truss. MBHS aim at preserving the graph size. And then the second one is MBHC. Select an edge contained in many triangles with trussedness at least k, but few triangles with trussedness less than k. And MBHC aim at maintaining the global clustering coefficient of the graph. Next is our save the neighbor heuristic, or we call SNH. Aims to reduce the number of deleted edges by deleting the unnecessary subsequent deletion of neighboring edges of an edge E that is selected for deletion. So it's select an edge E such that E is contained in many triangles in the maximal K truss, but the edge forming a triangle with E are not contained in many triangles. This is to limit the propagation to the triangle in M, in which an edge is likely to be deleted. And our exact algorithm is not applicable to the large graphs, since it takes exponential time. However, our heuristics can run much faster. So how can we evaluate the accuracy of our heuristic on the large graphs? For this purpose, we develop an lower bound algorithm on the size of optimal solution. If our heuristics are close to the lower bound, then they are effective as they are even closer to the optimal solution. The main idea of our lower bound algorithm is first to partition the graph into edgewise disjoint cliques, and then apply the best available lower bound on edges to remove from each clique, and next to compute the lower bound on the size of optimal solution. The bound is not tight, but is close to optimal solution in practical. In our experiment, we use 10 real networks. We call the first 5 small networks and the right 5 large networks. For experiments on synthetic data, please see the paper. We compared our algorithm with two baselines, ATK and GTK. The ATK removes all edges of trussedness at least k. We use it to see how many edges are saved by our methods. And GTK removes the edges with the highest trussedness until there is no K-truss in the graph. We use it to show the effectiveness of our heuristics and the efficiency impact of our data structure. We also report the result for the exact algorithm and the lower bound algorithm LB. We measure the ratio of deleted edges on small networks. Our heuristic finds a near optimal solution, which close to the OPT, and the lower bound computed by the LB algorithm is not far from OPT. We also measure the ratio of deleted edges on large networks. Our heuristics are fairly close to the lower bound, which implies that they are even closer to the optimal solution. In addition, they substantially outperform both baseline, and the exact algorithm did not terminate in one day. Next, we measure the relative error of the global clustering coefficient. CG is the coefficient before deletion, and CG prime is after deletion. Where MBHC, which aim to preserve the global clustering coefficient, outperforms all other methods. In terms of efficiency, our heuristics are 1 to 2 orders of magnitude faster than GTK because they employ the Truss decomposition update data structure. And MBHS is faster than MBHC, and SNH is slower, as expected by their time complexity. And last, ATK is very fast, but the least effective, and the LB took less than 10 seconds. That's all. Thank you for listening this video. Bye.